Welcome back to the video course on fluid mechanics. In the last lecture, we were discussing about the boundary layer formation and how the laminar boundary layer is formed for a flow over a flat plate. Then we have seen how the transitions to turbulent boundary layer, and we have also seen fundamental definitions for boundary layer, like say boundary layer thickness, then displacement thickness, momentum thickness, energy thickness, and then related theories. So today we will be further discussing about the first about the turbulent boundary layer, and then various theories behind the boundary layer, and then how we can get some solutions for various parameters as far as boundary layer is concerned. So first let us now see the turbulent boundary layer. So we have already seen how a laminar boundary layer is formed. Say for example, when we consider flow over a flat plate, you can see that initially, as we have already seen earlier, initially the flow will be say laminar in nature, and then later the flow become turbulent. So here, as we have already seen earlier, so here there is a flat plate lying here, and then say free stream velocity, free stream flow comes like this, and then we have seen how a boundary layer is formed like this. So we have already seen initially it will be laminar, and then we can see that there is a transition here, and then we have a turbulent boundary layer. So we have already seen some of the important aspects as far as laminar boundary layer formation is concerned. So now we will see some of the important aspects as far as turbulent boundary layer is concerned. So here now, say as I mentioned, when the Reynolds number is increased, the flow within the boundary layer undergoes a transition from laminar to the turbulent regime. So as we have already discussed in the case of a flow over a flat plate or a flow through a pipe, in all these cases it can happen initially. It can be laminar boundary layer formation, and then as the Reynolds number increases, then turbulent boundary layer formation takes place. So here, as far as the difference between laminar and turbulent boundary layer is concerned, so this figure shows the difference in velocity profiles for laminar and turbulent boundary layer. So this is say just like in the case of a flow over a flat plate, as we have already seen. So here this velocity is on the x-axis and depth on y-axis. So here the laminar boundary layer is concerned, you can see that it is just like in a very, say as in the case of parabolic variation, just like this. Turbulent, you can see it is just say much more in this direction. So this is the if you differentiate between the laminar boundary layer and the turbulent boundary layer, then with respect to y versus the velocity variation is like this. So now say we have already seen how the transition taking place with respect to a flat plate. So initially when the free stream velocity say touches or hits on the leading edge of the flat plate, it is say just due to the shear effect and then viscous effects, a boundary layer is formed, and then this transition from laminar to turbulent flow, if we consider the flow over an airfoil, so as you can see here, an airfoil is considered. Say we can see that the free stream velocity is coming here, and this is the airfoil, and then the boundary layer formation takes place, and then you can see that this is the laminar layer, and then after some time, say disturbance starts, and then this here we can say identify this is as the transition point, and then finally as we have seen in the earlier cases, say how the turbulence are created, so that we have discussed in earlier lectures. So the boundary layer now transforms to turbulent like this. So if we consider the flow over an airfoil, at some point laminar flow and boundary layer develops eddies, and as we can see gradually become turbulent zone after a transition point. So this is that transition point as explained in this figure. So the occurrence of transition point is say depending upon various parameters. So it depends upon the shape of the body over which the flow takes place. Say it will be say different case with respect to say flat plate, flow over a flat plate, or flow over an airfoil, or flow over a cylinder or a sphere. This transition, that means from laminar to turbulent boundary layer transition, will be different at different locations depending upon the shape of the body, and then also the fluid inlet velocity, and then the viscosity of the fluid. Like that, many parameters are here. So here in this figure you can see this is the transition point in the case of an airfoils of this shape. So here you can see that the shape of the airfoil is changed from upper figure here to this figure. The shape of the airfoil is changed. So here you can see that the true laminar flow this is called true laminar flow airfoil. So you can see that laminar flow is up to this point. But in this case you can see the airfoil, ordinary airfoil, here you can see the size is here larger. So you can see that the transition point is much before as in the case of, or much ahead of the laminar as in the case of laminar flow airfoil. So here the transition point is here, but in the case of ordinary airfoil like this, when the shape changes you can see that the transition point or the changes from laminar to turbulent takes much earlier, and then you can see this is the transition point. So that means this the changes from laminar boundary layer to turbulent boundary depends upon the shape of the body over which the flow takes place, and then the inflow velocity and many other parameters. So that we have to consider while dealing with these kinds of problem. So now depending upon the problem we can say identify when do these changes taking place, say from laminar to turbulent, or when this transition starts. So a number of experiments, especially the flow over a flat plate shows that critical value of the Reynolds number signifies the change of flow in the boundary layer. So when the Reynolds number changes from say particular range to other range, the boundary layer, the transition starts, and then the laminar boundary layer becomes turbulent boundary layer. So the case of especially for flat plate, a number of experiments shows that this can be in the range of 3 into 10 to the power 5 to 6 into 10 to the power 5. So this is the critical value of the Reynolds number, where the changes the transition starts depending upon the various other conditions, which can be between 3 into 10 to the power 5 to 6 into 10 to the power 5 Reynolds number. So it also depends on scale of turbulence, on laminar flow condition of leading edge, and roughness of the boundary profile adds its curvature and pressure gradient. So as I mentioned, say the boundary layer formation definitely depends upon the nature of the surface over which the flow takes place. So if it is more rough, then the boundary layer formation will be totally different than a smooth surface. So this the critical Reynolds number where this transition takes place also depends upon the say the boundary profile and then roughness of the boundary. So but anyway, most of the experiments which is conducted, which is reported in literature, shows that when the Reynolds number is less than 10 to the power 5, most of the time it will be laminar boundary layer. And then you can see that as in the case of laminar flow, here in boundary layer also, laminar boundary layer also, say when the Reynolds number is less than 10 to the power 5, then you can see that the boundary layer is much stable. So since it is a laminar boundary layer, it is very stable, and so we can say an average value of, say, based upon various experiments and reported say theories in the literature, we can say that the average value of the critical Reynolds number where this transition starts can be put as 5 into 10 to the power 5 as reported in many of the textbooks on fluid mechanics. So now if the boundary of the wall is very smooth, as I mentioned, the boundary layer formations and also its stability and its development depends upon whether the surface over which the flow takes place is smooth or rough. So if the boundary or the wall is very smooth, the turbulent boundary layer has a very narrow zone very close to the boundary. So as we can see, when the surface is very smooth, we will be having very narrow boundary layer. So narrow zone very close to the boundary in which the flow is still laminar, this narrow region is known as laminar sublayer. So even in the case of, say, wherever the boundary layer is turbulent, say if we consider a flat plate as we discussed earlier, so even say after some time the boundary layer can be turbulent, but still just very close to the boundary layer, especially say if the plate is very smooth, then you can see that there will be a narrow layer where the boundary layer is still laminar. So this is called a laminar sublayer. So here you can see that this is the flow over a flat plate. So here the flow is coming in this direction, and then the boundary layer thickness is plotted like this. So this is the leading edge of the plate, So here initially, as we have discussed here, the boundary layer is laminar, and then a transition takes place here, and then this is the turbulent zone, turbulent boundary layer zone. But still, for this turbulent boundary layer zone also, in the case of very smooth plate especially, you can see that there will be a small sublayer which is called laminar sublayer. So this laminar sublayer is forming because the transverse movement of the particle must die out in the laminar sublayer. So there will be, with respect to the fluid movement, there will be transverse movement of the fluid particle also. So that will be dying down with respect to the this very near to the flat plate or very near to the surface. So that is why this laminar sublayer is formed. So now we can say that say if we consider the flow over a flat plate as we are discussing here. So initially there is a laminar boundary layer, then there is a transition boundary layer, and then turbulent boundary layer. But even for the turbulent boundary layer also, we can identify a very small thickness of the laminar sublayer. So this also we have to consider, but most of the time when we discuss, since this effect of this laminar sublayer is very small and that thickness also very small, so generally this laminar sublayer may not be considered. Depending upon the accuracy we need, we may not consider this laminar sublayer in most of the calculations, but if very correct, very exact results are required, then we may consider the laminar sublayer also. So this turbulent boundary layer, as we can see here, so after the transition the boundary layer thickness is increasing. So the turbulent boundary layer thickness increases in the downstream direction from the leading edge of the plate, as we have already seen in the say in the previous figure here. So from the leading edge the boundary layer thickness is keep on increasing. So say as far as turbulent boundary layer is concerned, experiment shows that especially for flow over a flat plate, shows that the boundary layer thickness increases in the downstream direction from the leading edge in proportion to x to the power 0.8. So here you can see that this is x is starting from this location. So this increase is with respect to x to the power 0.8 is in the downstream direction from the leading edge in the proportion to x to the power 0.8, where x is the distance from the leading edge. And similarly for laminar flow, this boundary layer thickness delta varies in proportion to x to the power 0.5. So here you can see this variation, generally it will be x to the power 0.5, x is starting from this location, x to the power 0.5, and this turbulent zone is concerned, this variation is proportional to x to the power 0.8. So this experimentally we can show. So also through various experiments and also say in the literature we can see that if delta is the boundary layer thickness at a distance x in the case of turbulent boundary layer, then we can show that this delta by x is equal to 0.37 u infinity, which is the free stream velocity, into x by nu, the kinematic viscosity, to the power minus 1 by 5. So this is equal to 0.37 divided by Rex to the power 1 by 5, where Rex is the Reynolds number at location x. So since this quantity is with respect to the Reynolds number, so the delta by x, that means the with respect to the boundary layer thickness, and x the distance from the leading edge, we can show that this is equal to delta by x is equal to 0.37 divided by Rex to the power 1 by 5. So here you can see, say from here this x starts, and then this delta by x is with respect to this boundary layer thickness to the distance from this location to that particular location. And when we consider Rex means the Reynolds number at this particular location, where we consider the boundary layer thickness. So this is as far as flat plate is concerned, the experimental observation by various investigators. And then say if you consider the boundary layer with respect to the laminar and turbulent, say if you plot the boundary layer thickness and then the shear stress, then you can see the variations are plotted in this slide here. The characteristic of boundary layer thickness, delta and wall shear stress, tau w is, say here this is delta on y axis and x this direction with respect to x. So laminar is concerned, this is the variation boundary layer thickness, and turbulent, as we already seen, it is going like this. And then if you plot the wall shear stress, you can see that it will be, say laminar is concerned, initially it will be very high and then it will be coming down, and then say it reaches a minimum point, and then as far as turbulent region is concerned, again it is slightly increasing and then it will be again decreasing like this. So this is generally as far as a flat plate is concerned. With respect to wall shear stress, the variation is as far as laminar boundary layer, and turbulent boundary layer is concerned, the variation is like this. So now this is what we have observed so far is with respect to a flat plate. So as I mentioned, the boundary layer can develop in the case of internal flow like in the case of a pipe, or external flow in the case of the flow or a flat plate, a flow over a sphere or a flow over a cylinder. So the boundary layer formations can be in the case of external flow as well as internal flow. So before we discuss various theories and some of the equations as far as boundary layer is concerned, we will see how the variation takes place with respect to pipe flow, which is an internal flow. So here you can see that this slide shows, say, the pipe flow, the flow is coming from, if you consider the distance from here. So this is, say, we can say that let us assume here the potential flow regime. So then, say, with respect to the shearing effect and then the viscous effects, you can see that a boundary layer will be formed, and then, say, we can here you can say that this is the boundary layer flow, and after some time you can say it is a fully developed flow. So flow gradually transits from laminar to turbulent in the case of pipe flow like this. So you can see that this is, say, with respect to the no-slip condition of the pipe wall. So this boundary layer is formed, and then you can see that it is becoming a fully developed flow. So initially when the flow is entering is at this location, and if you consider a potential flow regime, and then after, say, we can say it is here this blue color indicates the boundary layer flow, and the variation with respect to the velocity we can plot like this. So finally the flow become fully developed with respect to the boundary layer formation. So as in the case of what we have seen earlier in the case of a flow or a flat plate, very similar way we can explain here for flow through the pipe, which is an internal flow. So you can see that as the flow enters the pipe, the boundary layer will initially be laminar. So we have seen the flow over a flat plate. Initially at the leading edge the boundary layer is laminar, and then there is a transition, and then finally the boundary layer become turbulent. So very similar way the case of pipe flow also, initially the boundary layer will be laminar, and then this will change depending on the ratio of the inertial and viscous forces. So in the pipe flow is concerned, say, laminar boundary layer to turbulent boundary layer, the change takes place depending upon the ratio of the inertial and viscous forces. So laminar flow is concerned, viscous forces are high, and turbulent is concerned, inertial forces are high. So you can see that the flow will be, as far as pipe flow is concerned, as we discussed earlier, the flow will be laminar when the Reynolds number is less than 2000, and a transitional flow regime will be between 2000 to 4000, and beyond 4000 Reynolds number the flow will be turbulent. So here we can observe earlier, say, here the, say, initially laminar, and then finally a flow become fully developed or fully turbulent here, as you can observe here. So say when the Reynolds number approaches 4000, the flow become fully turbulent, and then we can say that flow is fully developed in this case for the flow through the pipe. So the boundary layer develop, and also initially laminar to it is transits to the turbulence. So now we have seen the flow over a flat plate like in the case of a flow external flow, and also flow over a airfoil, and then now we are seeing the flow through pipe, which is the internal flow regime. So now we will see how we will derive the equations for the boundary layer, say, with respect to various theories, and then we will discuss how to get expression for various parameters as far as boundary layer flow is concerned. So the initial theories on boundary layer proposed by Prandtl, and then various other scientists like Blasius, say, have solved the boundary layer problems, and then tried to get expression for velocities, shear, and other parameters. So first we will see here the Prandtl's boundary layer equation, and then we will discuss how the Blasius got his solutions, and we will see then momentum integral equation as far as boundary layer is concerned. So Prandtl showed that the Navier-Stokes equation, which we have discussed earlier, can be simplified to get approximate solution for the boundary layer. So boundary layer, we can see that lot of changes takes place, and then he tried to use the Navier-Stokes equation, which were developed by the end of the 19th century. Prandtl tried to use this equation to solve the boundary layer. So, according to Prandtl, the flow can be divided into two regions, that is first one is within the boundary layer and then say above boundary layer. So, first one according to Prandtl, the flow is divided into two regions. First region is region of boundary layer, which lies in immediate neighborhood of solid boundary and within which about 99% of velocity change takes place and velocity gradient is normal to the solid boundary. So, here say for example, del u by del y is very large. So, where these Navier-Stokes equations are valid. So, we have already seen the Navier-Stokes equations. So, Prandtl divided the flow into two regions, one region where the boundary layer formation takes place, that means we, as per the definition which we have already seen for boundary layer, where the velocity change is in 99% up to that thickness is the boundary layer thickness which we define. So, this first region where this boundary layer is thickness is concerned. So, in that region say Prandtl showed that say this Navier-Stokes equation are valid and then we can directly apply the Navier-Stokes equation, and then he defined a second region outside the boundary layer which constitutes the main body of flowing fluid, which has velocities of the order of free stream velocity u infinity. So, the free stream velocity is coming and then above that say the boundary layer. So, he considers as separate region which is outside the boundary layer. So, this constitutes the main body of the flowing fluid and which has velocities of the order of free stream velocity u infinity. So, flow in this region, second region, the flow in this zone is governed by potential flow or ideal fluid theory. So that we can simplify the problem. So, through this proposition, say by this Prandtl assumption, actually the solutions as far as boundary layer is concerned has become much easier, since the boundary layer is concerned, it has to be solved using the Navier-Stokes equation, and then he proposed that beyond the boundary layer, so we can use the potential flow theory. So, which is much easier to deal with than the Navier-Stokes solution which we have discussed earlier. So, then with respect to this, the boundary condition for the analysis of the flow in the boundary layer are say the existence of no slip condition at the boundary, that is for y is equal to 0, u is equal to v is equal to 0. So, here as we have seen, so if you consider the boundary layer flow over a flat plate. So, here the region 1 as per the Prandtl's theory is here, this is region 2. So, here the boundary conditions, say when we consider this region 1 and region 2, the boundary condition here are the existence no slip condition at the solid boundary. So, that here at this location we can say u is equal to, say at y is equal to 0, we can say u is equal to v is equal to 0. So, this is one boundary condition, and then say outside the boundary layer the velocity u tends to become equal to the free stream velocity u infinity. So, that we can say that for y greater than or equal to delta u is equal to u infinity. So, here when we consider here this boundary layer, at this boundary layer location, we can see that at y is greater than or equal to delta, Prandtl proposed y is greater than or equal to delta, u is equal to u infinity. So, which is the, this is the u infinity, which is the free stream velocity. So, like this he divided into two regions, region 1 and region 2, and put forward the boundary conditions, and in this region where the boundary layer formation takes place, that region he used the Navier-Stokes equation, and beyond this potential flow theory can be applied, and then with respect to this assumption he tried to solve the boundary layer problems. So, in the region outside the boundary layer u tends to u infinity, and since there are no large velocity gradient in this region, the viscous terms same in the Navier-Stokes equation vanishes. So, you can see that outside the boundary layer the viscous term effects are not there. So, we can easily solve say outside the boundary layer. So, ignoring the body force component. So, as far as the Navier-Stokes equation is concerned, we have already seen the Navier-Stokes equation. So, Prandtl ignored the body force component in the Navier-Stokes equation, and then in the x direction for flow outside the boundary layer is reduced to del u infinity by del t plus u infinity del u infinity by del x is equal to minus 1 by rho del p by del x as in equation number 1. So, where this u infinity is the free stream velocity, t is the time, and p is the pressure, rho is the density of the fluid. So, this is the after this equation comes after ignoring the body force component in the Navier-Stokes equation. This equation is valid for flow outside the boundary layer. So, this is the first equation, and then for steady state flow the pressure P is a function of x only. So, the earlier equation is with respect to for transient condition. So, if we consider the steady state, then del U by del T is equal to 0. So, for steady state flow the pressure P is a function of x only. So, del P by del x is equal to, we can write dP by dx. So, hence from equation 1 we can write u infinity del u x by del x is equal to minus 1 by rho dP by dx as in equation number 2. So, this equation we can see, this is the equation outside the boundary layer. So, finally, this is transformed in this form by putting del P by del x is equal to dP by dx. So, u infinity del u x by del x is equal to minus 1 by rho dP by dx, equation number 2. So, this we can integrate. So, if we integrate this equation number 2, we can write P plus half rho u infinity square is equal to a constant as in equation number 3. So, this constant we can find out with respect to boundary conditions. So, the pressure distribution is a non-potential flow is determined from the above equation. So, this equation we can utilize to find out the pressure distribution, since generally the free stream velocity will be known. So, once the free stream velocity is known in the potential flow region outside the boundary layer, we can solve this equation number 3 to get the pressure distribution. So, this is the condition, the region 2 where the Prandtl considered the flow outside the boundary layer. So, then inside the boundary layer, now as we discussed, inside the boundary layer Prandtl considered the variations in the flow, and then he considered the Navier-Stokes equation as such. So, we can write, say if we consider 2-dimensional flow, the Navier-Stokes equation inside the boundary layer we can write as del u by del t plus u into del u by del x plus v into del v by del y is equal to minus 1 by rho del p by del x plus nu into del square u by del y square, where u and v are the velocity in x and y direction, rho is the density, p is the pressure, and nu is the kinematic viscosity of the fluid. So, this is the equation inside the boundary layer as forwarded by Prandtl. So, now if we consider steady flow using equation 2 and 4. So, here we have seen the equation number 2 here. So, for steady state flow using equation 2 and 4 we can write this del p by del x term we can write with respect to the earlier condition as derived in equation number 2. So, we can write u into del u by del x plus v into del u by del y is equal to u infinity du infinity by dx plus nu into del square u by del y square as in equation number 5. The Navier-Stokes equation y direction, after a certain order of magnitude of various quantities, we can show that this del p by del y is equal to 0 as in equation number 6. So, now the y direction is concerned, we have del p by del y is equal to 0. So, now in the continuity equation, now the remaining equation is continuity. The continuity equation for 2-dimensional flow we can write as del u by del x plus del v by del y is equal to 0 as in equation number 7. So, now these are the equations as far as the boundary layer is concerned. We have already seen the equations for the potential flow which we considered outside the boundary layer. So, this equation 5, 6 and 7 are known as the Prandtl's boundary layer equations subject to the following boundary conditions. So, this equation number, so 5, this equation number 5, 6 and then 7. So, these equations are called Prandtl's boundary layer equations subject to the boundary conditions are at y is equal to 0, u is equal to 0, v is equal to 0, and at y is equal to infinity outside u is equal to u infinity. So, or y is equal to delta also. So, as we have seen here at this location here, this is say here u is equal to u infinity. So, of course, outside the boundary layer it is free stream velocity, but here in this location also say we can write at y is greater than or equal to delta, u is equal to u infinity. So, these are the boundary conditions as far as the Prandtl boundary layer equations are concerned. So, equations 5, 6, 7 and the boundary condition as we discussed, this together we can use to solve the boundary layer problems. So, based upon this, these equations, the boundary layer equations were put forward by Prandtl at the beginning of 20th century, and then this has helped a lot to derive the approximations as far as the velocity variations, pressure variations and shear variation in the boundary layer. and many people tried to solve these equations, and in the one of the important solutions put forward by Blasius is discussed here. So, the Blasius solution for laminar boundary layer over a flat plate. So, in 1998, Blasius derived a simplified solution as far as flow over a flat plate, which is most of the time a typical problem which people consider to get a solution for this kinds of problem. So, the Prandtl equation with the boundary conditions are solved here in terms of u and v. So, Blasius also tried to solve the Prandtl's equations, but here again Blasius considered some more approximations. So, here the pressure P is taken as that in the free flow at the edge of the boundary layer, and as according to Blasius this can be considered as known, and then Blasius considered 2D two-dimensional steady incompressible flow over a flat plate at 0 angle of incidence with a uniform flow velocity of u infinity. So, these are the various conditions which are considered by Blasius, and then according to Blasius, since the plate is flat and has a negligible thickness and is uniform. So, according to Blasius, this pressure gradient del P by del X in the x direction, that means in this direction, this is here, the x direction is here. So, this is x direction. So, del P by del X as per according to Blasius, this must vanish as far as flow over a flat plate is concerned. So, according to the Blasius reformulated the Prandtl's boundary layer equations, and then he wrote for the boundary layer the Prandtl boundary layer equations were changed in this way. So, he has written u into del u by del x plus v into del u by del y is equal to nu into del square u by del y square. So, Blasius neglected this del p by del x, so that he got this equation number 1, u into del u by del x plus v into del u by del y is equal to nu into del square u by del y square, and then with this he used the continuity equation del u by del x plus del v by del y is equal to 0. So, these are the equations used by Blasius to get a solution, equations number 1 and 2. So, the Blasius solutions which is developed in 1908. So, he used these equations which we have seen here. The Blasius approximated the Prandtl's boundary layer equations, and we have seen the equations. So, he tried to derive an analytical solution or a approximate solution for this, the Prandtl's modified equations. So, he used the stream function psi by putting u is equal to del psi by del y and v is equal to minus del psi by del x. So, he used the stream function approach here. So, he put forward u is equal to del psi by del y and v is equal to minus del psi by del x. So, he derived the for various parameters by putting this u is equal to del psi by del y and v is equal to del psi minus del psi by del x in these equations, equation number 1 and 2, and then he used the various transformations, and I am not going to the details of this derivation put forward by Blasius. These derivations are given standard textbooks like fluid mechanics by R. A. Granger. So, finally, here we will discuss the various results put forward by Blasius. So, Blasius showed that the boundary layer thickness delta for the case which he considered here the flow over a flat plate, he showed that this delta is equal to phi into square root of nu x by u infinity, where nu is the kinematic viscosity. So, Blasius got delta is equal to phi into the square root of nu x by u infinity as in equation number 3, and then he tried to get the solution for the Watt shear stress. So, Watt shear stress can be written as tau 0 is equal to mu del u by del y at y is equal to 0. So, after substitutions he showed tau x y at 0 is equal to half rho u infinity square into 0.66412 divided by square root of Rex, where Rex is the Reynolds number at that particular location as we considered earlier from the leading edge of the plate. So, that is equal to 0.3320x rho u infinity square by square root of Rex, where u infinity is the free stream velocity, rho is the fluid density, Rex is the Reynolds number at that particular locations. So, these solutions which is obtained by Blasius, he also experimentally verified this. So, almost it was matching with respect to the experimental observations, and then he derived the local skin friction or dimensional skin friction coefficient as Cf is equal to tau xy at say 0 divided by half rho u square, that is equal to 0.664 divided by square root of Rex. So the total skin friction coefficient as derived by the Blasius is CDF is equal to 1.328 divided by square root of REL, where REL is the Reynolds number at the trailing edge of the flat plate which we considered, or this is equal to D by CDF is equal to D by half rho U square L. So here the D is the total, the drag is concerned, we can D is equal to integral 0 to L tau xy at 0 dx is equal to rho u0 infinity square integral 0 to L 0.33206 dx by square root of Rex, and then finally Blasius got the explicit expression for displacement thickness and momentum thickness. So he derived the displacement thickness as delta star is equal to 1.73x by square root of Rex, and theta is equal to 0.664x divided by square root of Rex. So like this Blasius derived expression for the boundary layer thickness, then displacement thickness, and then the momentum thickness. So using these expressions we can easily get other parameters like the velocity variations, and also we can get the shear variation as we have seen in the previous slide. So like this same Blasius solved the boundary layer equations proposed by Prandtl, and then by certain approximations. So if you plot the Blasius boundary layer profile, you can see that we can plot say u by u on the x axis, and here u by mu x to the power half into y. If you put this eta here, so this variation as proposed by Blasius will be like this: at u by u is equal to 0.99, at eta is equal to 5, variation will be like this. So this shows the Blasius boundary layer profile as far as the flat plate which he considered here for this case. So like this the boundary layer problems were solved by Blasius by approximating the Prandtl's boundary layer equations. So we have seen the boundary layer equations proposed by Prandtl, and then also we have seen the proposed solution by Blasius, and then another important equations or another important theory proposed for which we can see in the boundary layer literature is momentum integral equations. So here the boundary layer flow analysis is based on the momentum principle derived by von Karman by integrating the Prandtl's boundary layer equations. So again the von Karmans use the Prandtl's boundary layer equations, and then he tried to integrate it so that he got an equation called the momentum integral equation. So this momentum equations derived from equation of motion by integration over the boundary layer thickness known as momentum integral equation for boundary layer flow, or this is also called von Karman integral equations. So basically von Karman used the Prandtl's boundary layer equations, and then he tried to integrate from 0 to delta. Say for example, if we consider the flow over a flat plate as we have already seen here. So here what von Karman tried to do is he tried to integrate with respect to 0 to, so if this is 0 and then delta, so between the boundary layer thickness he tried to integrate the Prandtl's boundary layer equations, and then these equations are called the momentum integral equations, or also called von Karman integral equation, as it was derived by von Karman. So the for this purpose the control volume used by von Karman is say here you can see that this is the flat plate and the free stream velocity is coming here, and then he considered a control volume like this. So this is the boundary layer which is formed here. So the variation from 0 to like this. So von Karman considered a control volume like this, and then he tried to integrate. So with respect to this figure, so here you see that the integration is between 0 to delta, so that within the boundary layer. So boundary layer equations which are derived by Prandtl are here. So if we consider unsteady state or transient flow, then the equations are del u by del t plus u into del u by del x plus v into del u by del y is equal to minus 1 by rho del p by del x plus nu into del square u by del y square. That is equation number 1, and then the continuity equation del u by del x plus del u by del y is equal to 0. So von Karman tried to integrate this equation 1 with respect to y with respect to the depth, as we can see with this is the y direction. So with respect to this only von Karman tried to integrate. So, after integration within the limit of 0 to delta, we can write del by del t integral 0 to delta u dy plus integral 0 to delta u del u by del x dy plus integral 0 to delta v del u by del y dy is equal to minus 1 by rho integral 0 to delta del p by del x dy plus nu integral 0 to delta del square u by del y square dy, equation number 3. So, from calculus, so now this equation you can see this is Navier-Stokes equation in two dimensional force. It is complicated equation. So, we had to use certain techniques to get say the momentum integral equation as proposed by von Karman. So, from calculus we can write this integral 0 to delta del uv by del y dy can be written as this is equal to integral 0 to delta u del v by del y dy plus integral 0 to delta v del u by del y dy. So, this is coming from calculus, and now hence we can write integral 0 to delta v del u by del y dy is equal to say uv within the limits of 0 to delta minus integral 0 to delta u del v by del y dy as written in equation number 4 here. So, here if you use equation number 2, which is the continuity equation, this equation, now we will use this continuity equation here in this equation number 4. So, that we can write this term integral 0 to delta v del u by del y dy is equal to minus u infinity. So, the u at the delta, that means at the edge of the boundary layer is u infinity. So, minus u infinity, which is the free stream velocity, integral 0 to delta del u by del x dy. So, this v at this location we can write as with respect to del u by del x dy from the continuity equation plus integral 0 to delta u del u by del x dy as in equation number 5. So, here now this approximation is put in this earlier equation number 3 here. So, if you put here substituting 5 into equation number 3 and noting that, so here we use the Newton's say law of viscosity. So, tau is equal to mu du by dy. So, and noting that tau is equal to mu du by vanish that y is equal to delta, we get as we can write this equation number 3 as del by del t integral 0 to delta u dy plus integral 0 to delta del by del x u square dy minus u infinity integral 0 to delta del u by del x dy is equal to minus 1 by rho dp by dx integral 0 to delta dy minus tau 0 by rho. So, here rho is the fluid density, tau 0 is the wall shear stress at the bottom of the plate, and then u and v are the velocity in x and y directions, and delta is the boundary layer thickness. So, this now this equation number here, to get a solution, not actually a solution, actually he derived this momentum integral equation. So, he considered the steady state problem. So, he used the Leibniz rule here, and then second and third terms of equation 6 we can write here, second and third terms here, this second and third terms von Karman wrote like this: integral 0 to delta del by del x of u square dy is equal to d by dx of integral 0 to delta u square dy minus u infinity square d delta by dx, and he wrote u infinity integral 0 to delta del u by del x dy is equal to u infinity d by dx of integral 0 to delta u dy minus u infinity square d delta by del x. So, now using Leibniz rule and then using the definitions of delta star, the displacement thickness, theta the momentum thickness, and u infinity del u infinity by del x is equal to minus 1 by rho dp by dx. Finally, von Karman derived the momentum integral equation. So, he derived this equation as tau 0 by rho is equal to d by dx of u infinity square theta plus delta star u infinity d infinity by d u infinity by dx. So, this equation is called momentum integral equation in 2 dimensions. So, this say was derived by von Karman. He used the Prandtl's boundary layer equations, and then he used some transformations and used Leibniz rule, and actually this equation is for the steady state conditions, and he used the various assumptions, and also he used the fundamental definitions for the displacement thickness and momentum thickness, and finally von Karman got the momentum integral equation as tau 0 by rho is equal to d by dx of u infinity square theta plus delta star u infinity du infinity by dx. So, this equation is called momentum integral equations or von Karman momentum integral equations. So, now This you can see that von Karman did not get a solution for the problem, but he transformed the Prandtl's boundary layer equation to another form of the equation called momentum integral equations. So, again this momentum integral equation, to say our purpose here is to get a solutions either in terms of velocity or shear stress or in terms of boundary layer thickness or displacement thickness, etc. But what based upon the Prandtl's equation, what von Karman got is the momentum integral equation, which is an equation connecting the what shear stress, then the free stream velocity, momentum thickness, the displacement thickness, and the variation of the free stream velocity with respect to x. So, this is the expression which was obtained by von Karman by using the Prandtl boundary layer equations. So, now to get a solutions, we have to say explicitly, now this equation is quite implicit, it is having various terms like displacement thickness, tau 0, then momentum thickness and the u infinity and its derivations, the free stream velocity and its gradient. So, to it is not explicitly giving a solution. So, we have to use say either put some assumptions, or if we know some measured values of say boundary layer thickness or the velocity or the wall shear stress or the displacement thickness, then we can find out the other parameters. If one or two of the parameters are not, then remaining parameters can be found. So, the momentum integral equation is quite general and holds the laminar and turbulent flow. So, this equation are valid for laminar as well as turbulent flow, and provided velocity distribution u x y is known. So, the velocity variation in x and y directions are known, then we can say this generalized equation of momentum equations, we can it holds for laminar as well as turbulent flow. So, to get the solutions, we say generally either we can start with a approximation for the velocity distribution and then try to find out the boundary layer thickness or the momentum thickness or the delta star, the displacement thickness, or we can start with these parameters delta star delta and then come back to the velocity. So, the result of integration of momentum equation, ordinary differential equation for boundary layer thickness. So, using this we can get important characteristics of boundary layer. So, you can see in various textbooks on fluid mechanics, just like in the case of Granger and others, you can see how this momentum equation is used to get various parameters as far as boundary layer is concerned. So, this is a general expression as far as connecting various parameters. So, generally what we can do here, so as shown in this figure. So, here this figure shows the boundary layer profiles which we can use. So, the velocity u by u infinity with respect to y by delta, we can use various approximations like whether it is linear, or we can use the what is proposed by Blasius, or we can use the cubic variations, or we can use the parabolic variations, etc. And then we can assume this velocity variations and then we can substitute back to the equations, the momentum integral equations, so that we can find out the other parameters. So, this is the general way of solving these kinds of the problem using the momentum integral equations. And then the pressure distribution in the boundary layer is concerned. Outside the boundary layer, in the main flow, from the Prandtl's equation we have already seen u infinity du infinity by dx is equal to minus 1 by rho dp by dx. So, here pressure does not vary in y directions. So, same pressure exists in the main flow and transmits to the boundary layer. So, we can say that external pressure is impressed in the boundary layer. So, as far as pressure distribution in the boundary layer is concerned, we can use these expressions, and then you can see with respect to this assumption here, we can say that the external pressure is impressed in the boundary layer, and the pressure does not, as far as this assumption is concerned, the pressure does not vary in the y direction. So, here you can see if say the flow surrounding a cylinder, you can see the free stream velocity and if the pressure variation, the streamlines are plotted. So, flow around a circular cylinder, streamlines are shown here, and also the pressure variation, the pressure distribution around a circular cylinder is plotted here for various conditions. So, here P0 plus half rho u square, and then here P0 minus half rho u square, here P0 minus rho u square, P0 minus 3 by 2 rho u square, where this capital U is actually the free stream velocity, u as in the earlier notation it was u infinity. So, here capital U is the free stream velocity. So, we can plot the pressure distribution also. So, here now with respect to the what we have observed here, say what we have discussed so far is the Prandtl derived the boundary layer equations, and then various people tried to solve it by various assumptions, including the moment integral equations, and then the pressure variation also can be found by using the various expressions.